Now we will work on another differential operator identity. Show that um, curl of V is equal to the gradient operator acting on the divergence of V minus the Laplacian operator acting on V, where V is a vector field and del square is the Laplacian operator. Okay, so we're going to start with writing the curl of V using the subscript summation notation. So here is our del operator. So we're going to take the curl of V. So we have curl of the vector field V here we're considering. And using our subscript summation notation, one way to write this is epsilon ijk, Levi-Civita symbol, the jth component of the gradient operator. So we're going to put the gradient operator here and take its jth component. And then we will take the k component of the curl. So we have the second vector here, that's curl of vector field V. We're taking its kth component, and this has to be in EI hat direction. So first vector, epsilon ijk, jth component of the first vector, kth component of the second vector, which is curl of V, and then we have EI hat. All right, and now this is a Levi-Civita symbol epsilon ijk. Now how do I write the jth component of the del operator? Del operator is del xj ej hat, but its jth component is just del xj, partial derivative with respect to xj. And then how do I write the curl of V? It is epsilon, we're looking at its kth component, so it is epsilon klm. Now we're taking the lth component of the gradient operator, which is del xl, and then mth component of the V vector field, V sub m, and this is all in EI hat direction. So curl of V is normally epsilon klm del xl Vm in ek hat direction, but we're taking the kth component, so there's no ek hat. So we have this term. Now I'm going to regroup this so that I have the Levi-Civita symbols written as a product in the first term here, epsilon ijk, and then I have epsilon klm, but you can see that klm, lmk, so this is the positive direction, clockwise direction is positive here, so epsilon klm is equal to, let's note it here, epsilon lmk, due to cyclic permutations, so this is epsilon lmk. And why am I doing this? I want to use the Levi-Civita identity. In order to be able to use that, I have to have the common index in the same position in the subscript. Okay, and then I have del xj, and I have del vm, mth component, del xl, EI hat. All right, now we're ready to use the Levi-Civita identity. Kronecker delta first indices I and L. Kronecker delta second indices J and M minus Kronecker delta inner indices J and L, outer indices I and M. Firsts, seconds, inners minus inners, outers. Multiplied by del xj, and then we have del v sub m vector field m component partial derivative with respect to xl in ei hat direction. And now this is going to dictate that L's are replaced by I. So that's the first term here. So this is going to be L's replaced by I and J's replaced by M. So if J's are replaced by M, del xj will become del xm, partial derivative with respect to xm. And then I have the partial derivative of Vm with respect to xl, but L has been replaced with I now, so it's del xi, and this is in ei hat direction, minus, now the second term, we're going to replace L's with J, so this J will stay, del xj, and M's will be replaced by I, so this will be del vi, partial derivative with respect to del x, not L, but J now, J is equal to L, in ei hat direction. Now I can see that what I have here is the derivative, partial derivative with respect to xi. I can change the order of the derivatives here. ei hat, this is my del operator, acting on the partial derivative of Vm with respect to xm, which is the divergence of V. Then I have the second derivative, del square Vi ei hat, is my vector field with respect to xj. And now I'm reading the first term here. It's the gradient operator. This is the gradient operator multiplied by divergence of V minus Laplacian operator acting on V. So basically, what I see here is exactly this. So let's copy that there. This is our final result, which was what we were supposed to prove. Okay, so let's go over this step by step. We're looking at the curl of vector field V. The curl of a vector is epsilon ijk, jth component of the del operator, kth component of the vector in ei hat direction. That's one way to write it. And now the jth component of the gradient operator is del xj. The kth component of the curl is epsilon klm del vm del xl. So del xl, lth component of the gradient operator, mth component of the v vector field. And we don't have ek hat because we're looking at the kth component. This is all in ei hat direction. Epsilon klm is equal to epsilon lmk due to cyclic permutations klm, lmk, and mkl. They all give the same thing. So we can write epsilon klm is epsilon lmk and then use the Levi-Civita identity First indices Kronecker delta IL, second indices Kronecker delta JM minus inner indices J Kronecker delta JL, outer indices Kronecker delta IM, del XJ, del BM del XL EI hat. The first term tells me J's will be replaced by M. So this will be del XM, del VM, and then L's will be replaced by I, del XI, EI hat, minus, then I will have L's replaced by J. So del XJ, M's replaced by I, del VI, del XJ, EI hat. Now I can change the order of these derivatives. Del xi ei hat, and then I have del vm del xm. So this is my gradient operator. This is the divergence of v minus, here I encounter the second derivative with respect to xj of the vector field v, which is my Laplacian operator.